Hey, Peter.
Hey Manu, how are you?
Good, good. Living the life. How about you?
Summer's coming to an end. Time to page in everything that I've forgotten in the last 3 weeks.
You took you took some time off?
Yeah, I was out for like it was 2 weeks, so it wasn't
Nice.
that much. But and it's typical. Like the first week while you're off, you're still sort of thinking about everything and writing the odd spec and doing email. And then the second week, you get into it and then you get back and it's amazing. You have no recollection. It's like, what was I doing before I left?
Well, good for
Uh,
you. You know, time off is necessary. Yeah.
it is, and it was. I probably should have taken time earlier, because when you get too exhausted, right after a while, it takes a long time to recover.
Tell me about it. Yeah.
Yeah. So I didn't. I think if I remember correctly, you were going to talk a little bit about
Yeah,
what
that's
how
what,
Shaz does and so on.
yeah. I mean, if it's just the two of us, it's a little bit silly, but more than happy to, at least it's recorded, so I guess it can go on the record, by definition. But maybe
Sure.
we can give the others a few minutes to see if they're joined.
Yeah, give folks time in that. I mean, you can decide if you. Oh, there we go. Hey, Mark.
Mark, what are you doing here?
I think you have a workaholic problem, Mark. You're
You're
supposed to be
supposed to,
on vacation.
I
yeah,
just can't stay away from you guys.
dude, you're supposed to be off.
Nah, this is
We
more
were
fun.
just we were
This
just
is more
saying,
fun. It's still early. I haven't had a holiday ahead of me.
Okay,
well, good to
we
see
need.
you.
I could see you too. You were just saying?
That Peter and I were discussing, taking time off and coming back and having to re-engage and rejiggle all the neurons and stuff. So, but obviously you can't take time off, so you can't get off. So,
No,
go
today
ahead.
I'm just observing here, so I'm
Okay.
still on vacation, so
All right. So you want me to talk? Yeah, well, thank you for the opportunity for sure. So I think I'll get started. Hey, Hank and Eric. Hey, guys.
Hi there.
Hey,
Hey,
morning.
Nate.
I don't know how many more people we'll have, but so I'll start, right? I'll grab the screen. Um, so, I mean, thanks, Mark, am I sharing the right thing here? Yeah. Oh, how do I? Sorry, I'm gonna turn off my camera because otherwise I'm gonna be all sideways here. There we go. You guys can see my screen?
Yes. Authenticity, confidentiality, and privacy.
Yep. Yeah. So the I talked with Mark at IETF, and we had talked a bit before, but I've tried for the past 18 24 months or so to plug myself into the IETF, understand how it works and how we can bring our work there. But I've always had a challenge because we have a very different approach to the problem. Our company, we started this company on the idea of fixing kind of the overall architectural problem of solving information exchanges between two parties, regardless of what these parties are. And so it's a very top-down approach. Over the several past sessions on workload identity, we've talked really bottom-up. And so when I talked with Mark and stuff, I realized that maybe we have indeed something to contribute by explaining this top-down approach and how it addresses some challenges like the ability to attest not just chips, but also people and organizations and data information. And then the composition, the business logic, the verifiable business logic that verifies a composite, a set of multiple attestations, evidence of different types. All of those challenges, if you approach the problem top down, they kind of solve themselves. At least that's what we discovered as we were building this infrastructure. So this work is real. This is an infrastructure that is in production right now. So you guys can go and play with it if you want. It's very bare bones, but it's m.sh. It is right now what we have is a messaging application called Messaging, and it enables people to create information spaces and exchange information through them. It's fully authentic, confidential, and private. But the unlike Signal, which is really end-to-end encryption, the mesh is really about any agent to any agent, and the agents act on behalf of different types of entities. And so the reason, let me just because this is recorded and before I need to set some context, right? The reason we are in the CCC also is that we want to make this capability available and present it to everyone. We are, for that purpose specifically, we are a public benefit corporation. So the intent is to partner with a consortium of companies to be able to operate this as a public benefit infrastructure. We are also a NATO Diana innovator, and we've been pulled into the rapid adoption program within NATO. NATO is dual use, right? So it's not just defense, but it's also for civilian protection across NATO. So the match between what we do and RATS and the other efforts around confidential computing is really, when we look at this diagram, for us, what we see is a bunch of entities, the owners, the verifier owner, the relying party owner, the relying party itself, and then there's information flows that are flowing between all of these guys. And the verifier in the middle is basically taking all those pieces of information and then has some business logic and then spits out results to another entity. All of this looks very much like, if you break it down to each one of its components, it's Alice and Bob trying to exchange information to one another. And if you want the output of any verification to be reliable, so that a relying party can actually make a decision on it, you need to make sure that all the pieces that come into that composition, into that output, were in fact verified and coming from a known source. So the reason we started the company is we realized that what we have today, this IT-centric approach and the web in general, is not verifiable, virtually impossible, because the architecture of the web itself relies on, hold on a second, to record your screen and system audio, I guess, allow. I don't know if this was properly recorded so far, but and so what we, given the fact that the web is inherently delegating authority to privileged insiders, and all security models are at the domain level, not at the independent entity. In fact, there is no such thing as an entity on the web. Everything is a resource within a domain. We thought that, okay, so that's a challenge. What we want to solve is any entity to any entity with a verifiably secure, direct, pairwise, cryptographic relationship between two entities across domains, across nations, across untrusted networks. The idea is to establish the infrastructure that enables that connection between any two entities. Because if we can do it for two, then we can repeat, rinse and repeat, and we can chain them. And if we have chains of cryptographic chains that are verified, then we can put them stitch them together, chain them together for chains of authorities, chains of data custody, communications, command control, all that good stuff. And once you have a chain, a cryptographic chain, then you can use the chain to then bootstrap other relationships, direct relationships between any two entities. And that's where kind of a mesh infrastructure emerges, hence the name of our company, Hush Mesh, a cryptographic mesh overlay network over the internet. And what's interesting is when you approach the problem top-down, saying, I don't remove all middlemen, I want Alice and Bob to have an independent existence and to be able to enter into a relationship that will, once established, will be independent of everything else, you discover some immediate requirements. The first one that was most insightful or shocking to us was that, not shocking, but like most profound to us, is the need for a unified and universal identifier space that is not under the authority of any entity. So you need an identity space or identifier space that is, randomly generated, that is not, controlled by anyone. You'll see, I'll get back to that later in this presentation. You see how we do that and how we actually use that as roots of trust then to bootstrap everything else. The next thing is that any one of these entities, if there is nobody else, if there's nothing else, those entities needs to have their own cryptographic keychains that are completely unique, so that every entity can establish relationship with any other entity. And the corollary to that is that if you want to have privacy, then those entities, although they have a unique identifier, right, within the system, they need to be able to generate and manage and juggle an unlimited number of aliases for each one of these relationships. So by default, if a relationship has to be, if you want privacy to be preserved, each one of these relationships needs to not be correlatable. You need to make sure that by default, it's not correlatable. And you can introduce correlation if you want to. So if you want to have, an identifier that's recognized across multiple entities, then of course you can use that. And then the other piece is that, if Alice is about to share private or confidential information with Bob, Alice must have assurance that Bob is equally equipped to protect that information once it's been shared, once it's been transferred. So very quickly, you see that the problem is really a symmetrical problem where the relying party and the attester very much are. You need to flip the model. The relying party should actually attest itself to the attester, also because the attester should not be releasing sensitive information to a relying party that it's not known or a secure relationship and able to protect that information. And then if you want to do that across any type of entities, for all types of entities, then the assurance is not just mutual, it should be global. And that's why we said, okay, now we need to build a global infrastructure. It's not just within one domain, it's across domains. And of course, it can also be implemented within one domain or one ecosystem in isolation, but really the value becomes, how do you establish that across virtually any domain and all domains? And then last week, I think we talked about Mark, you had mentioned the need for 6 nines in a verifier infrastructure, where if you want to remove that dependency on a always-on 6-9 reliable infrastructure, then what you realize is that you need to have, private ledgers for each one of those entities so that they can keep their own established and credentials and reference values that they need to verify other things and all that good stuff. And they need to have it in a way that's tamper-proof, that is itself inherently verified. And then finally, if you do the effort of doing all this, then you should do it in a way that systematically minimizes attack surface and follow the path of least trust. We don't believe, zero trust is a nice principle. We don't believe that zero trust is, of course, fully achievable. There's always an initial verifier. And so that's why we call it least trust as opposed to zero trust. So I'll walk through a couple of steps here that unfold the way that we basically came up with this architecture. And then I'll go into the math or the cryptography that enables these ledgers and enables the identifier bindings and stuff like that. So imagine 2 entities, and these can be, of course, in the context of this TWI group, these can be workloads, but again, it could be Mark at JP Morgan pushing a workload onto a specific machine, right? That's the chain of authority, a chain of custody where bits get moved across the chain. So the entities can really be anything. So the first thing we said is that the entity should not go and be connected to a domain that has insiders. So it has to connect to something that's going to act on its behalf that will be verifiable. That's what we call the agents. So it's a little bit, it may be confusing, I think, with Spiffy and Spire, although I think that the role of the agent here can actually be collapsed into the role of the Spiffy agent also. But more generally, it's a piece of software, an executable that is going to act on behalf of an entity. So as we said, the first thing that these agents should do is be verifiable. So we use hexagons to refer to a TEE, a trusted execution environment, that will be cryptographically verifiable. So the first thing that the agent needs to do, if you want to have a one-to-one relationship so that the agent can truly act on behalf of that entity and no other entities, and that no other agent can act on behalf of this entity, the agent actually needs to be the identity server, if you want, the identity agents. It needs to enroll and identify its entity, but also it, of course, needs to adapt to its protocol. So different types of entities have different protocols. We see the protocol layer as, almost irrelevant. For this thing, we can support virtually any type of protocol. You just develop an agent that supports that protocol, as long as the agent can do the enrollment and the identification of the entity itself, and then, of course, authenticate this entity when it comes back to its agent to do something, then you're good to go. And then if we want this agent to be able to protect the information that the entity is going to give it, then this agent needs to be able to manage keys on behalf of the entity. And so it's going to have not just credential keys or certificates and private keys with certificates, but it will also have encryption keys so that it can literally encrypt the information of the entity with keys that are unique to that individual entity. And so you do that for one entity, then you do the same thing for any other entity with different types of agents that map, right? And that can be developed to map the types of entities that they connect to. And as we said, those entities, those agents independently, of course, it doesn't do you any good for the connectivity. What we said is that, what first thing we should do is we should verify them. And what we discovered when we started building this up is that the first thing that was useful to do was to separate the business logic that's custom to the entity. So the different protocols, the business logic and the processing of the information and the management of the entity itself to the agents. That's the great thing. And then the key management itself, we actually moved it to the verifier. The verifier is also running, of course, in our architecture in a TE. It's actually a local TE on the same machine, so that we don't have to worry about being on a separate platform. So that initial verification of the agent is really like a inherent physical binding of these two TEs on the same platform/chip. And the key management, we moved it to the verifier. So that's why you see the encrypted, storage there being in blue under the verifier. And what that gave us was then the ability to say, great, now we have a verifier, we need to verify the verifier. And that gave us the insight, okay, now we can actually create a chain of verification. The verifier, the top verifier, again, then can verify its children. And it has, because it does key management for its children, it can pass a key to its children, to each of its children. And so the key that is passed by the parents to the child can then unlock the keys that the child is using to secure the information of the agent on behalf of the entity. So that gave us a pattern that could be repeated to create chains of verification that are independent of the type of entity that we are trying to verify. And each one of these verifiers now has its own, keys, so it can encrypt information, not just on behalf of its children, but also for itself. So it has now the ability to have a secure, cryptographically tamper-proof local storage, if you want. And local, of course, is cryptographically local, if you want. And that pattern can then be repeated. The other thing I need to mention, right, those hexagons here are not just single machines, right? We're talking about clusters of machines. All this is running right now in the Azure cloud. And all those hexagons are, auto-scale clusters of confidential compute, virtual machines running on Intel SGX. will support TDX and others. We're just going to develop other agents to support those different types of attestations. So this still does not give us the connection between entity A and entity B, but the natural next step to be able to bridge this was to realize that what we can do then is use the same pattern and introduce a shared verifier. So basically continue the chain of verification for each branch. But if we have a shared verifier at the top, then we can use the verification chain to enable key exchanges through a verified infrastructure. So there is no exposure of, because every one of these attester verifier relationship result in the establishment of a secure connection, a TLS connection, plus a individual entity key that's being exchanged between the verifier, each verifier and its attested children. We now have path to do key establishments between any two agents so that the agents can then exchange a pairwise key and then can now have a secure link for each individual entity that they act on behalf of. And then you're going to ask, okay, great, but these are, this is all key exchange. Now, how do we enable the ad hoc connection or discovery of those entities, and how do we enable or trigger or bootstrap the key exchange? We basically use external aliases. So the identifiers of a workload, for instance, of a human or of an organization, the publicly visible identifiers are, in our world, aliases that can then be resolved, and I'll talk about that also a little bit later, into this unique identifier for each entity that turns out to be a random identifier that is completely shielded from the outside world, that will be used for cryptographic bootstrapping. Then, agent A can, an alias can be created, or an existing alias can be used. It can be a spiffy ID, or it can be virtually anything, a random ID, a UUID, whatever it is. It can be registered in the shared verifier. Then the entity B can resolve that alias if it received it out of band or explicitly programmed in the agent. And then the agent B can then go up the chain, its chain of verification, and then go and retrieve and resolve that alias, and then find the agents that registered it, do a key exchange, establish a relationship. So you see that the role, what we discovered is that the role of the shared verifier in this infrastructure now is augmented with a kind of a naming registry. So we call it the universal name system because it resembles the DNS, but it really is for any type of entities, not just domain names. And then because the shared verifier then verifies the children and recursively all the way down to the verifier of the agent, we also realize that this is equivalent to a certificate authority, essentially, because we give cryptographic credential to the children all the way down to the agent. And in fact, to interact with the web, because the web is relying on conventional certificate authorities in the browsers, we needed to be able to issue certificates, X509 certificates. So we do that. Every single agent that exists in the mesh today that interact with the web receives its own X509 certificate through the UCA, and the UCA is itself anchored with Let's Encrypt. So we get automated signing of our the root certificate of the mesh, and then we can have chains of certificates all the way down to agents that can be recognized on the web. So this pattern, essentially, if you look at the global hexagons here, there's not a single human in it. There is no admin, there is no access to any information. All bits that are generated and managed and verified throughout that little block there, this little pattern is completely isolated from the outside world, 100% running in TEs. And what's interesting is that the pattern is also recursive. So in a second, I'll show you how we then can scale it up and scale it out by just repeating the pattern over and over again, which basically grows the mesh without increasing its software attack surface, because it's essentially the same verifying code that exists throughout the entire infrastructure. It's really the agents that bear the brunt of adapting this network to the type of entities. So the first thing that we had to do, obviously we need to bootstrap some initial agents and some initial verifier infrastructure. But the first thing we had to do is, how do we deploy other types of agents? So how can we grow this mesh network with other verified agents? And so the first thing we realized that we had to do is to plug the CI/CD pipeline to a custom agent, right? We call it the factory agent, that essentially takes the output of the CI/CD pipeline. And the CI/CD pipeline currently is, in our implementation, doesn't run in a TE yet because it's too big for SGX, so it will have to be in TDX or in SEV or whatever. But essentially, the CI/CD pipeline includes, in our implementation, includes a stage at which we load. So we take the source code directly from the repos. We compile it. We inject, in fact, a bunch of configuration bits in the source code itself before we compile it, so that all that gets burnt into the resulting fingerprint, as we call it. So we load it in a TE. As part of the CI/CD pipeline, we get the evidence from the attestation enclave, and then we use that evidence, that kind of reference evidence, if you want, as the reference value, which we call the fingerprint. And then the factory agent goes and registers that in the UNS as kind of the UNS record, if you want, that would enable then a deployment agent that can be deployed anywhere else in the mesh to go and retrieve that those reference values in the case of the traditional TEs, to then do the verification of the newly deployed agents. And the deployment agent literally just starts this new enclave and then does the attestation of that enclave and then deploys another, what we call it, another verifier behind it. That's too deep for now. But anyway, so that's how we can then verify the successive recursive deployment of additional verifier enclaves and additional agent enclaves that enable us to support different types of use cases and entities and all that. So as I said, right, this pattern of attesters, verifiers that are kind of agnostic of the type of verifications that they do and that do the key management on behalf of their children result in this attester and verifier network with an initial verifier at the top, which we call the UNS UCA a little bit ago. And then the UNS UCA capabilities, by the way, can actually, because each one of these verifiers has the same capabilities to generate keys for itself, to encrypt information for itself, can then encrypt part of the repository, so that we can also distribute the UNS UCA functions or registries, if you want. And we can delegate them, which is super important for the resiliency and the scalability and performance of this infrastructure. If you had indeed just one single top-level UNS UCA type infrastructure, or verifier that could be the brittle thing, then you would need that 6 nines reliability. But we can achieve that if we can actually distribute all the values, reference values, and information as close to the edge agents as possible. And then, as I said, you deploy agents. Now it enables you to just chain together, all kinds of things. So as I said, Mark at JPM deploying workload, on a specific server. It could be, Alec at Microsoft, certifying that this specific machine is in a testing, right? That a specific machine is in a French data center, for instance. It can be, Neil at HushMesh that is basically testing or working on behalf of HushMesh, deploying a verifier so that machine can be verified, through the mesh infrastructure. All of those chains of cryptographic chains can now be deployed with a single recursive, repetitive, repeatable, mechanism. And if you take this diagram and you fold it onto itself, now you see why we call this a mesh infrastructure, because essentially any one of these agents, either through a chain or through direct introductions, can then establish automatically through the infrastructure a direct connection with any other agent on behalf of any individual entity. And the infrastructure in the middle, once the relationship has been established, doesn't need to be involved anymore. Of course, you can, refresh the attestations, rotate the keys, but all of that just becomes programmatic. It doesn't need to be done by humans, and it can be done, programmatically based on the type of use cases, the type of entities that are being, managed by the edge agents. So what we are building is, a series of agents that enable us to plug different types of entities. So if you go to m.sh, you'll see that, as a human, you'll be automatically, a keychain is going to be generated for you. You won't see it because it's managed by your agents. Then it's a chat application. So we create chat spaces. We are currently finalizing the organization agent, so we can register organizations in the mesh. For NATO, they're very interested in sovereign agents, so registering nations in this infrastructure, so that you can have a chain of authority that is terminated by representative of a nation, so that they can attest and certify, let's say, regulations or any other digital asset that needs to be used in other verification chains. We have a file system agent, so any human that meshes up, we say mesh up instead of uploading. If you mesh up a file, there's a file agent that's going to create for each individual folder files. We'll create a unique identifier, and then we'll encrypt it with keys bound to this identifier, so that all files now become entities within the network itself and are all made available to virtually everybody. But of course, one thing I didn't mention, authorization is also done at the relationship level, so that, if Hank comes to my house and I want to, Hank wants to borrow my car, I can give my key to Hank. The authorization, the passing of those credentials is in the relationship between me and Hank. Nobody else in the world needs to know any of it. So really, authorization, credentialing, essentially, it's all done with cryptographic credentials under the hood. Not the web verifiable credentials, but inherently native, cryptographic credentials between agents, and all of that, can then talk to one another. We can connect IoT devices, and then of course the next stage of all this is to be able to connect agents that AI agents that will be able to work on behalf of any other of these entities, and then be backstopped, right, by a cryptographically verifiable consent flow and authorization flow that can then be enforced by the agents and by the cryptographic backbone here. So I don't know why this is here. So I don't know, I guess, oh, I'm going the wrong way. So that's why I'm pressing the wrong key. So I'm sorry, it's a little bit longer than I thought it would be, but this is the math behind it. And this was the most compelling insight. What we realized is if you create these identifiers, and again, right, the identifiers I'm talking about, we call them STEM IDs. They only exist within the TEEs. And that's because we realized they had to be randomly generated because we didn't want any central authority to assign identifiers, and we didn't want to have to deal with collisions across an infinitely large space of potential entities. And so we said, great, we're going to randomly generate those identifiers, and then we're going to make them large enough so that they're not only just an identifier, but they're also a cryptographic key. And that's when we realized that if we do that, if the identifier of an entity is in fact its own primary key, then we can derive other keys, and we can create a keychain that unites everything. So that's what you see represented in that expression there. We use the hash symbol as a shorthand for the HMAC function. So if an entity, an agent, uses its verifier to create a key for its entity, for a specific entity, that is what we call the STEM ID. You can think about it as a STEM key, a key from which all other keys stem. And then we can hash that key using an HMAC function to derive an unlimited number of other keys. And so you can, for instance, use a relationship ID. So if I want to have a relationship on the mesh with Peter, my agents can use my STEM ID and use the relationship ID that Peter's agent is giving to my agents to create a unique key that will represent my relationship with Peter. And then within that relationship, I can use any key identifier, again, social security numbers, whatever folder name, SPIFFE ID, whatever it is, and you can chain, and this is also recursive, right? So you can string together, just like you had domain name, resource, and resource name in web URLs. You now have a method to derive an unlimited number of keys that creates a structured information space. And for each one of these, cryptographic URL, if you want, it results into a key that enables you to encrypt information in what we call a cell, a cryptographic cell. The encrypted data is in fact a cell, but it's encrypted with a unique key that can only be recovered by the software agent that has access to the STEM ID. And so that gives us a mechanism by which we can cryptographically isolate an unlimited number of information for an unlimited number of entities. We call that process the process of encrypting information with a key that's derived from a STEM ID. Instead of having to use all these words, we created the word STEMcryption. And what's important here is this additional sentence here that it's authenticated encryption. So it's an encryption that's based on a key, but using an authentic encryption scheme. So it gives us, in fact, the repeated, authentication every time there's a message, every time there's a communication that passes. You have that zero trust, continuous authentication type mechanism. And it's with keys derived from a STEM ID. So it's mathematically bound to the identifier of the entity. But what's important here is that it's not just directly derived, but it's also keys that may have been themselves encrypted. So it can be a fresh key that is encrypted with a key that's derived from the identifier. The reason why it's important to have it in the definition of STEMcryption is for key rotations, because of course the HMAC function, you can't change anything. If you change one bit, you get other keys. So if we want to have keys that can be long-lived to secure information that is long-lived on behalf of an entity that may be long-lived, you need to be able to rotate keys without having to rederive or have a completely new path. So essentially, the derivation path becomes the identifier, the long-lived identifier of something, and then the keys that are STEMcrypted, the fresh keys that are STEMcrypted with that derived key, becomes the layer at which you can do key rotations. And this is what it results into. And it's quite stunning when this infrastructure started working for the first time. This is an actual snapshot of some of the registries or the database that is attached to one of these nodes in the mesh. And so the data, the bits on the right are the STEMcrypted bits that belong to some entity. We, the operators of the infrastructure, have no way to correlate it back to anything because the identifier, what we call the cell ID, is itself derived from the encryption key. So we have it's a one-way function. There's no way to correlate any of those bits to any of the entities or even the agents. And all of that is completely shielded from the outside world. So now you have an information space for each individual entity that is completely shielded from all other entities and all humans in a way that is globally and cryptographically verifiable. And so to come back to then the question, as I mentioned, right, all the identifiers within the infrastructure are only exclusively managed within verified TEs. To bridge that to the outside world and the existing web, we can use the same STEMcryption function to then bind any type of identifier. It can be a UUID, it can be a social security number, it can be an email address. You just have to add in the key derivation function from the STEM ID, you can add other elements within that key derivation that will bind all that stuff, all that context to the resulting key. And so the way you resolve this then is by using the agent STEM ID itself. So let's say I'm using you guys, if you go on m.sh, you're going to use your email address to, get in. By doing that, it creates a keychain for your email account under the cover, so that we can then bind that, create a relationship between you as a human and that email account. And then the agent that's going to resolve that email address will use its own STEM ID to encrypt, to stemcrypt, right, the email address using a specific scheme here. We, of course, hash the com and then the domain name and then the user ID, so that we can also have intermediate hashes there that can be used across organizations, across other things. So we respect kind of the authority hierarchy of the web and other authority hierarchies that are out there. But essentially, we can use the same stemcryption model, because the agents can stemcrypt the STEM ID of the corresponding entity using its own STEM ID and the external alias in the chain, in the derivation chain. So anyway, I know this is a lot, and this is quite deep in the first introduction, but this is recorded, so we can go back to it later. And so the question, of course, is how in that architecture, the weak link is the STEM ID of the initial verifier, because we can't export that thing, because of course you would have to trust us, managing that initial verifier secret that encrypts the keys that are passed to the children and so on and so forth. So at the very top, what we realized was we could use a Shamir secret sharing vault. So itself is built on a bunch of very, very tiny enclaves. I think it's just a few thousand lines of code. All of this is Rust code, by the way. And so we have what we call guardians, and the guardians are keeping facets of or shares of the STEM ID. In fact, there's a layer on top of that, but we have a keystone, which is a random number, and blah blah blah. Anyway, there's a Shamir vault on top, and the intent of the Shamir vault was to then be able to geographically distribute that and let different organizations, nations, or like large financial institutions, or nonprofits, whoever, manage guardians independently, so that now we have global, how to say that, a way for people to just trust that we, the operator of that top node, the initial verifier, do not have access to its primary secret. All of these guardians talk to one another. They chat constantly to verify that everybody's there. If some guardians go away, we have an M out of N or a K out of N threshold, and then you can spin up new guardians, regenerate new facets or new shares to maintain the durability of that initial secret. And then that basically then cascades down. The verifiers verify everybody else, just like I explained, and that's what anchors the entire infrastructure. So as I said, if you guys want to play with it, send me a message. It's live. It's very bare bones right now, but it's quite functional, and we think it's pretty cool. So I'll stop here. Thanks, Eric.
Yep, no problem. Thank you, everyone.
So that's what we worked on for the past, about 3 years now. So.
All right, I'll go first because I have questions and nobody else raised their hand.
Go ahead.
Okay. So I was taking notes as you went, and really will be rewatching it, and we'll perhaps have additional questions. But so I think one of the notes I took, and I think you started answering is towards the end, but maybe you can walk us through this again. So there is always a bootstrapping problem, not just for an individual a node or a pair of nodes, but for a technology in general. And Peter, the recording is usually placed on YouTube under the Confidential Computing Consortium playlist.
There's a little bit of a The last few sessions were not there. I sent an email to Ryan yesterday.
Yeah, I saw that. We'll
Rian,
need to
yes.
fix
Yeah.
that. So we'll follow up. So some of my questions really relate to that. You know, how do we get this off the ground, right? And one of the questions I had was, so DNS has had a long and storied history. Like, you know, it's in broad use. It has some known issues, right? And at the same time, you know, we've learned so much. So speak a little bit about how you interact with DNS in this setup again, and how do you like? Yeah, it looks like you almost looks like you're a replacement for DNS, right? In some way, or are you overlaying it? I still didn't get sort of the architectural moorings there to name resolution.
Right. So we interact with DNS because we have to, because there is an external human, you know, an organizational authority hierarchy that exists that in fact enables us to do domain verification because, you know, it's a well-known thing. So what we do is that we don't replace the DNS today for sure. And, you know, not for a while. And I'm not, you know, obviously we are, you know, pushing the limits here, right? We're not pretending or assuming that we're going to replace the DNS anytime soon. So we basically map those domain names as entities within this infrastructure. So we do have today domain agents that can take a URL like, you know, hushmesh.com and basically hash that, has its own repo, its own, you know, ledger, its own registry, and then stemcrypts, you know, come as a first layer of the hierarchy, and that results into a key that results into a information space where we can store information about the .com, you know, level. And then under .com, we do another, you know, recursive hash where we basically hash hushmesh as a string, you know, and that gives us a key that enables us to have an information space for hushmesh.com as a domain. So for every URL out there, we can map the entire web topology or architecture with the domain names, even URLs themselves, right? Like slash, you know, spiffy, you know, domain.com slash, what did you have, you know, payroll application slash something that can be mapped by agents and result into a key that itself then can be used as a bootstrap key for an information space for that specific workload, for instance. So we don't replace DNS. We map domain names and the entire hierarchy of the web onto agents that transform that into a key that then can be used to then wrap another fresh key that can then be the root of trust for an information space for that that resource.
So if I want to locate another party, so I want to know if Peter, for lack of a more distinguished example, is onboarded to HashMesh or not. Is there a way to discover that?
Yes. So
without,
instance,
like, is it an in-band discovery? Do I need to get him on the phone and say, hey, you know, give me some information?
No. So we have about, you know, I think it's 25 or 30 different types of agents right now that precisely needed to map to the outside world. Because the first thing we need to do is the bootstrap problem for people to be able to get on the mesh as frictionless as possible, in an as frictionless way as possible. So if you go to m.sh, you'll see that email addresses are recognized. And similarly to the domain name, we have an email address agent that will then map that into an entity. That entity, in fact, corresponds to the account, the email account that has that email address. That, by the way, will be, right now we don't have it yet, but will be claimable by the organization that claims that domain. So it's essentially domain name, hash, username of that email address, and that maps to, you know,
when you say claimable, how do you prevent squatters, I guess?
The squatters, the domain verification will be done through the DNS itself.
I see. Okay.
That's what I implied, you know, by saying that we have an infrastructure that exists.
Right.
For domain verification by putting records in the DNS.
Yeah. Okay, so then another question I have, and I will then actually have 3 or 4 questions.
If I may just expand a little bit, because it may actually address the other ones. So in addition to email, domain, we have phone numbers. So that's to find the humans. And then to connect to external, workloads or applications or web, systems, we implemented OpenID Connect as an identity provider. So we can pass signed OIDC tokens, identity tokens to a web application.
Yeah.
And then we have a REST API agent in the mesh that enables you to, from a web application, to call back into the mesh. In the identity token that is passed to the web application, we add a random link code, as we call it. That link code was generated inside the infrastructure by calling the REST agents with that link code. Then we can chain you back to the originator, the human that meshed into that web application. So that,
Right.
And then we have a couple of other things like a file system agent and other things, right, as I said, that enables you to bootstrap things to a certain degree. Sorry, I wanted to.
Okay, no, this is good. So another question is, so say I am a convert to this whole concept of decentralized identity. Now,
Yep.
again, no comment on whether it's good or bad. I don't even know where it stands right now, but seems like a
Yep.
good idea. Do I get can I use that to receive a separate identity through you, or are you looking as a sort of a complete replacement for that?
So I would say both. We actually had a contract with DHS, the Department of Homeland Security, for those who are not US based. We built a prototype of a verifiable credential web W3C verifiable credential wallet on the mesh. So using the infrastructure. So essentially, we developed a wallet agent that is capable of receiving credentials from an issuer and then capable of presenting those credentials to a verifier. Sorry, the name is confusing. The W3C wallet thing calls the relying party a verifier. So we built that, but in the process of building this, what we realized is that the concept of a verifiable credential is really the only thing that's verifiable is it's in the credential itself. Everything else around is not verifiable. In our system, everything is verified and verifiable and verified, including the business logic of the wallet itself, including the keys that encrypt the information. So it's kind of every message that are being passed between two agents. By the way, it's a CBOR over WebSocket, but can support anything else. Every message that's being passed, because it is encrypted by a link key, which is authenticated encryption between those two agents acting on behalf of entities, they all inherently cryptographic credentials because they're all encrypted with keys that are bound to the sender and then decrypted by the receiver with a key that was pre-established with the sender. So we have all that capability already built in. So we can support the W3C, credential environment and ecosystem. Europe is very big right now on eIDAS and all that good stuff. But we actually recommend that we shouldn't build that kind of cryptographic infrastructure on the web, because now you reintroduce all these other non-verified, pieces of code and, CAs and, infrastructure where you don't really know where the keys have been. You cannot attest all the wallets and all that good stuff in our world. And then we had other benefits, is that the fact that you have a wallet that is built on network side, not just phone side, gave you all kinds of other very easy recovery. You can replace your phone and rebind it to your agent and all that good stuff. So there's lots of benefits in doing it network side as opposed to phone side.
Okay, so I down to 2 questions. In a distributed system like this, how do you introduce upgrades? So you need to fix bugs, you need to upgrade the protocol, you need to do it in such a way that you prevent, I guess, malicious introduction of bugs, right? So the question is, how do you phase in a change in something that if your success is probably global, right? So billions of nodes.
Right. Well, I want to be clear, right? We're not trying to take over the whole world at once, right? This can be deployed in small or smallish, like the relationship with NATO, maybe for a subset of NATO humans, right? Not all NATO humans. So it can be deployed at JP Morgan, or it can be deployed across an ecosystem of healthcare or other places. It doesn't need to be the whole world at once. But the idea, the way that we do it now for ourselves, which will then be extended so that we can enable other organizations to do the same, is that we simply push new releases through the CI/CD pipeline. I told you the factory agent is essentially creating a cryptographic record in the decentralized UNS, saying for this workload XYZ, which has a stable, long-lived, can be a spiffy ID, whatever you want, identifier, here is the next version of that thing as attested by whoever has authority over the CI/CD pipeline itself. As I mentioned, right now, we don't have the full loop. The CI/CD pipeline is not yet in the mesh itself, which means that we can't yet use the human identity and authentication that we have in the mesh to then be able to say, it's Neil at HushMesh who pushed this, this new version of the software to the factory, and then the deployment agent, can deploy it. So, but eventually that's what's going to be, right? Once we have the organization capability, and once we have the full chaining of humans, CI/CD pipeline on behalf of an org, then you're simply going to say, Mark, and maybe it can be a multi-sig, right? Before it gets put through production, it's Mark and Paul, and I don't know who your colleagues are. 3 of them needs to sign the push of this thing. The factory agents will only act on that thing if the business, the verification logic, right, checks out, and then it will create a record that will enable deployment agent to grab this and deploy it on the JPM, chain of trust, the chain of verifiers that has been deployed for your environment.
Yeah, but then do I need to then reestablish trust in this in every part of the network that needs to upgrade? I mean, right?
No, that's the thing, is that in fact, there's a longer discussion, and that may be with Hank or with, with all of us here. We had MITRE. MITRE is the, government nonprofit, a nonprofit that does service for the government. NATO Diana paid MITRE to take a look at our stuff. And they did a cryptographic analysis of the messaging primitive, and especially the attestation of a child by a parent verifier. And what we realized when they did the formal analysis of this thing, that it was critical that the child know that have in its code configuration information, and that it knew which parent it was going to connect to. Yeah. Because if it did not know that, there was some scenario, some path that could result in a child connecting to the wrong parent that could act as a man in the middle, and then connect to be in the chain of trust. So what we have is that the chain of trust, the recursive verifier infrastructure, is anchored at both ends. The code that gets deployed for, let's say, the JP Morgan chain of trust is burnt into the code itself. So you don't need to redeploy it every time. You only deploy the new revision of the software agent that gets deployed at the leaf, as the leaf of that chain of trust. That gets re-verified against the new record in the UNS, and that gets redeployed.
Okay. So I need to understand this a little better. We're out of time here. Yeah. Perhaps we should, put your questions on the mailing list, and perhaps we can finish this conversation next. I don't want to sort of drop it like this. It seems like the result. I also wanted to talk about how does this fit into whatever reference architecture we come up with, right? Yeah. So it needs to be one of the things the reference architecture handles. And again, we're out of time, so please, if you had any questions, I apologize, I monopolized with my questions, but let's get to them next time. And Manu, thank you so much for your time today. We'll make sure this recording is made available.
Sounds good. And you guys, get on m.sh and send me a message.
Okay.
You can leave it. You can try it right now. See you later.
M.sh.
M.sh, yes. It's the
All right.
it's the TEE that gets you literally your TLS connection from your browser, from your phone, is terminated into a TEE, and then it connects you to every other agents, including chat agents and space agents and audio video, connections and stuff like that. All of it
All right.
end-to-end encrypted with keys managed in it. All right,
Very
take care,
cool.
guys. Thank
All
you.
right.
Bye.
Take care. Bye-bye.